Ever wondered how AI systems like GPT or BERT achieve such human-like understanding? The answer lies in a revolutionary architecture that's reshaped the field of machine learning, the transformer. Today, we're diving deep into the inner workings of transformers, exploring their groundbreaking design, the math behind self-attention, and why they've become the backbone of modern AI. Let's break it down. Before transformers, recurrent neural networks, RNNs, and their variants like LSTMs dominated sequence modeling. But they had a critical flaw: sequential processing. Each token in a sentence had to be processed one at a time, making it hard to capture long-range dependencies and limiting scalability. Imagine trying to read a book by only seeing one word at a time. Your brain would struggle to grasp the context. That's the challenge RNNs faced. Enter the transformer, a model that abandoned sequential processing entirely. How did it manage to outperform its predecessors? Let's unpack its core innovation: self-attention. Self-attention is the transformer's secret sauce. At its heart, it calculates relationships between all tokens in a sequence, allowing the model to weigh the importance of each word relative to others. Here's the math. For a given token, the model generates 3 vectors: queries, keys, and values, using learned linear transformations. The attention score between 2 tokens is the dot product of their query and key vectors, scaled by the square root of the key dimension. This score determines how much focus a token should have on another. Let's visualize this. Suppose we have a sentence: the cat sat on the mat. For the word cat, the model computes its query vector and compares it to the key vectors of all other words. The resulting attention weights tell the model whether cat is more related to sat, action, or mat, location. These weights are then used to compute a weighted sum of the value vectors, producing a context-aware representation of cat. This process happens in parallel for all tokens, eliminating the need for sequential computation. But wait, how does the model understand word order? After all, the cat sat on the mat isn't the same as mat the sat cat on. Transformers solve this with positional encoding. Unlike RNNs, which inherently process sequences in order, transformers use sinusoidal functions to inject positional information into token embeddings. These encodings are added to the input vectors, allowing the model to distinguish between cat in position 2 versus position 5. With self-attention and positional encoding, the transformer lays the groundwork for its encoder-decoder architecture. Let's explore how this structure enables tasks like translation and text generation. The transformer's architecture consists of an encoder and decoder, each composed of multiple layers. The encoder processes the input sequence, transforming it into a series of hidden states that capture contextual relationships. The decoder then generates the output sequence, using self-attention to focus on relevant parts of the input and previously generated tokens. Each encoder layer contains 2 sublayers: a multi-head self-attention mechanism and a feed-forward network. Multi-head attention allows the model to learn different representations of the input by splitting the query, key, and value vectors into multiple heads. For example, one head might focus on syntactic relationships, while another captures semantic meaning. These heads are then concatenated and linearly transformed, creating a richer contextual representation. The implications of the transformer are staggering. From language models like BERT and GPT to image processing with vision transformers, this architecture has become ubiquitous. Its ability to handle long-range dependencies and scale efficiently has enabled breakthroughs in machine translation, summarization, and even code generation. But the journey doesn't end here. Researchers are constantly refining transformers with techniques like sparse attention and efficient variants for real-time applications. So what's next for transformers? The future lies in making them more efficient, interpretable, and adaptable to specialized domains. As researchers push the boundaries of this architecture, we're witnessing a new era of AI capabilities. If you're curious about the latest advancements, make sure to subscribe for deeper dives into cutting-edge research. Thanks for watching. Now go explore the world of transformers yourself.